Okay, today I'm going to be covering pushdown automatas and how they're different than finite state machines. Let's take, first of all, for example, the language that accepts strings a to the n, b to the n, for all n greater than or equal to 0. And using an NFA, we have best case scenario, something like this. We have a starting state at 1, we epsilon into 2, loop around with a onto 2 multiple times, epsilon to 3, loop through with b multiple times, and then epsilon to an accepting state. That would give us a's and then b's, but we could have multiple a's and less b's. So 5 a's, 2 b's, 1a, a million b's, and that does not fit in with this language. So what we need is a way to have a finite state machine with a form of memory, kind of like a cache memory for finite state machines. So PDAs. PDA is a finite state machine plus memory. Just like before with an FSM, we have an input string, controls within our finite state machine, such as transitions in different states, and now we have this new structure, a stack. The stack is what implements the memory, and since I'm talking to mostly programmers, the stack will look very familiar. Before we get too deep into how it works, though, let's go over some terminology and notes really quick. Center that really quick. Alright, notes. Same as in a finite state machine, PDAs use an alphabet for their input string called sigma. And now our new element or structure, if you want to call it, is the stack. Now the stack works just the same as a programming language stack would, but with a few kind of special rules involved. First of all, we can push to the top of the stack, we can ignore the stack completely, and we can read and pop from the top of the stack. Now, this is an important note because read and pop are combined into one operation for this type of stack. So in a programming language, you might be able to read the top of the stack without popping that element off, or pop that element and not even care about what data is in it. But in this implementation, reading and popping from the stack are all one operation. The stack has its own alphabet, just like the input string, which we call gamma, denoted by this symbol. And it can be the same as sigma. For example, if your sigma was A and B, your gamma could be A and B, though I don't recommend it because you probably just get confused. Examples of how a finite state machine works. In a finite state machine, you start with A and you transition, you start with state 1 and you transition into state 2 with the input of A. A is within our input string language, so we just transition right on over. That's a finite state machine. In a PDA, it's similar, but the stack has to be taken into account. So, in a, let's center this. In a PDA, you have your input string, or your input symbol. You have your second position in this new tuple. You have a second position and a third position. The second position is reading and popping from the stack, the top of the stack, and then this third position is what gets pushed to the top of the stack. So, to get from state 1 to state 2 in this particular example, A has to be our input symbol, X has to be at the top of the stack, and Y gets pushed to the top of the stack. So basically taking the place of X on our stack. Special note right here about a PDA is that you can only make this transition if and only if X is at the top of your stack. So this A is a prerequisite, this X is a prerequisite, and this Y is basically your output or your post condition for this transition. And NFA rules do apply to PDA. So epsilon has to be taken into account. Epsilon here can mean that no input is needed, just like for our FSM. If epsilon is here, we can just transition right on over, no problem, no input needed. It is the same for our PDA down below. In this second position, if you have an epsilon, it actually means to ignore the stack completely, okay? Not try and read an empty symbol, and I'll talk about that in a second. Ignore the stack. The same is for the third position. We're going to ignore the stack completely. We're not going to try and push anything to the stack. The reason we are ignoring this position here is because you cannot read or pop epsilon from the stack. So if you're looking to the top of your stack and trying to find an X and there's no X, that's a pretty easy for an empty symbol at the top of your stack, and therefore if your stack is empty, that's going to be basically the only time where that prerequisite is actually met. Alright, example time. Now that we know how PDA works and we have some terminology, let's go through a couple examples. Let's take, for example, again, a to the n, b to the n for n greater than or equal to 0, and then I have a couple of strings here that we're going to try to put into this PDA. Now we already tried it with NFAs and we know it doesn't work. Let's list a couple things really quick. Our input string language is A and B. Our gamma, or our stack language, is going to be X and Y. You could have 1, 0, hashtag, $, whatever you wanted to put. Special symbols basically is all you want, but I'm going to use just X and Y. The PDA, I'll go over really quick. Center this really quickly. We're going to have a start state at 1. Our epsilon for our input, so our input doesn't matter. We're going to completely ignore what's in our stack to go to 2, and we're going to push X to the top of the stack. From 2, if we have A as an input, and we're ignoring the entire stack, so if A is our input, we're going to loop back to 2 and push Y to the top of the stack. From here, after we've decided to do all of our A's and we want to transition to B, it is a complete epsilon transition, so this all of these prerequisites are met, nothing needs to be done, so we just wind up in state 3, where we can loop back on ourselves if B is our input and Y is at the top of our stack. Now, only if Y is at the top of our stack and B is our input can we make this loop back and we're pushing nothing to the stack. Finally, we can epsilon to an accepting state 4 using no input and only if X is at the top of our stack and we're pushing nothing to the top of the stack. Now here you can make note that the stack does not need to be empty when we are done with their string. If there was another accepting state in somewhere along the lines, we would still have data in our stack. If we were looking for a to the n, b to the n minus 1, we would at least have one more character in our stack when we finish this. And even if you have some data left in your stack, I drew up this little mini death state thing here where you can just epsilon to another state and then just loop back on yourself and just recursively kill all of the little symbols that are in your stack. So now we've covered that, let's go through these strings really quick. Okay. First things first, A. We're going to start out in state 1, epsilon with no input. We're going to ignore the stack and we're going to push, an example here, we're going to push X to the top of our stack. There's that. Now we're in state 2. We're going to using A as an input, we're going to ignore the stack, but we're going to push Y to the top of our stack. So Y here, we've read that in. We're going to do that 2 more times. So Y and y. So then we have, well, you can think of it as n y's at the top of our stack and x at the bottom. This is a special symbol we'll talk about in a second. This, you can already start to see the memory coming into place here. We have n y's, and as we here break them back down, we will have exactly the same amount of a's as b's. So we're all done with our a's. We're going to epsilon transition right into 3. Keep this stack in frame. Now we're in 3. We're going to use b as an input. We're going to check to make sure that y is at the top of our stack, which it is. We're going to pop it, and we're going to push nothing to the stack. So, and 2 more times as well. So now we only have x in our stack. We are done with our input. So we're going to go ahead and epsilon over only if x is at the top of our stack, which it is. So now we are in our accepting state, and this string is in our language. Let's do this other one really quickly. We're starting at 1. We're going to epsilon on over, put x at the top of our stack, which we already have. We're in 2. We're going to do a 3 times. We're going to put y 3 times. Okay, and now we've transitioned over using epsilon, met all the requirements. Now we're in state 3. B as an input. Y is definitely at the top of our stack, so we're going to remove it once and then remove it again. Now we have no more input characters or symbols, so we have no other choice other than to epsilon into our accepting state. So we take our epsilon transition, we go on over, but we do have to make sure if and only if x is at the top of our stack. So we go over, we check our stack or our memory, and y is at the top of our stack. This means that we are stuck in limbo, and therefore this string is not in the language of a to the n, b to the end. Now it is in a to the n, b to the n minus 1, which is just as impossible to calculate from a regular finite state machine. Therefore, Pushdown automatons. That is basically it. Thank you.